Okay, so you've got almost everything for nonlinear p-center problem on a tree network with duality. Nobody has done any work for general networks yet, so maybe if you get sufficient insights in this course, you might want to do that. There's only one thing that remains, that's the computation of the beta ij's, even though I gave you an insightful pictorial way of computing that. I think we need also some analytical expressions. So let's talk about that in this remaining time. Now, we had fj's with domains 0, delta I, fi with domain 0, delta I, and we have a monotone increasing function in this domain. We also have upper bounds. We assumed that each upper bound is not larger than the diameter of the tree when you put yourself in vertex I. Okay? So ui is less than or equal to delta I. If, of course, ui is greater than delta I, then you can make ui equal to delta I, and there will be no loss of generality. We also had one assumption. I assumed fi ui is less than or equal fj uj if I is a smaller index than j. That's just an indexing convention. It does not cause any loss of generality again. So the definition of beta was, it's actually the minimizing value, z1 value, for the one-center problem for the vertices I and j. So by definition, it's z1 value for vertex set I consisting of I and j only. That was the definition. Okay? Which means that beta ij is the optimal value of the solution to the minimization of, say, R subject to fi dx di less than or equal to R, fj dx vj is also less than or equal to I and j are specific indices here with upper bounds. So, assuming that the problem admits a feasible solution relative to the upper bounds ui and uj, then there will be an optimal value, optimal objective value for this, which is finite, so beta ij will be that. If the upper bounds are such that they do not permit a feasible solution, then of course beta ij is by convention plus infinity. Okay? All right. Let's define Aij to be the maximum of Fi0 and Fj0. Due to our indexing convention, this will be equal to Fj0 if you assume I is less than j. Okay. So let's look at these first. Okay. ui is a number between 0 and delta I by assumption number 1. Which means that it's in the domain of fi. So, each ui is in the domain of definition of fi. For this reason, the constraint which tells you that the distance between x and vi must be less than or equal to ui is true. In other words, x is feasible to this constraint if and only if I can apply fi to both sides, because both the left side and the right side are both in the domain of definition of fi, which means this is true if this is true. Now, what is the use of this? Well, the use of this is to make these constraints look like these, so I can actually start combining. Okay? So, from here, I can see that this pair of constraints is nothing but fi dx vi less or equal fi ui and fj dx vj less or equal fj uj. So, since those two constraints are equivalent to these, when you look at them in combination with the first two constraints, you've got fi dx vi less than or equal to r, and you've got fi dx vi less than or equal to fi ui. So, an equivalent definition of beta ij is then the following. Equivalent definition of beta ij is to require beta ij to be the minimum solution for minimization of r subject to fi dx vi less than or equal to minimum of r or fi ui. And similarly for j. Provided that r is greater or equal aij. Why do I need that? Well, because when you take the minimum here, you don't want r to be less than aij. In that case, of course, there is no feasible solution, and we're interested in the feasible versions of these. Okay? So you need to impose r greater or equal aij whenever the problem has a feasible solution. Okay? It wasn't in the problem definition before, but now we put it in. Okay. Now, can I say that minimum of r and fi ui is in the domain of definition of the inverse of fi? What is the range of fi? Well, it's a mapping from 0 delta I to fi 0 fi delta I. So the inverse function has domain defined by fi 0 fi delta I and range 0 delta I. So fi 0 fi delta I, I'm wondering if this number that I see is in this domain of definition. Is it or is it not? Well, there are two possibilities. Either R is the minimum or the other one is the minimum. If R is the minimum, we impose the condition R greater or equal Aij, which means that R will be greater or equal Fi0 or Fj0, it doesn't matter. And so it's going to be also, since R by assumption is less than or equal to Fi ui, which we know is less than or equal to Fi delta I, then it's in the domain. Okay? In the remaining case, Fi ui is certainly in the domain because ui is in the range from between 0 and delta I. Okay? So clearly, the minimum of R, Fi ui, is in the domain of definition of Fi inverse, provided that R is greater or equal Aij, or in this case Fi0. Okay? All right, so what's the use of this? It gives me the following. Minimum R subject to, I apply the inverse function to both sides because both sides admit the inverse function in the domain. So the left side outputs Fi inverse of Fi, outputs the xvi. The right side gives Fi inverse evaluated at minimum of R and Fi ui. How many parentheses do I need? 1, 2, 3, 4, 5. Okay, one more. And similarly, the other one. Provided AI is greater or equal R is greater or equal Aij. So here's the important conclusion. Beta ij is the smallest R for which these two constraints admit a feasible solution. Well, you're looking for a point x whose distance to either vi or vj is no more than these upper bounds. So what is the required condition for that? The distance between I and j, vi and vj, must be less than or equal to the sum of the upper bounds. Okay? Let's just write plus fj inverse of minimum of R fj uj. So let's define EI of R to be Fi inverse minimum of R Fi ui. That definition applies to every index, including j. Okay? And let's define Eij of R to be the sum of Ei of R plus Ej of R. So with this, what we're looking for is the following. We're looking for the smallest r such that the distance between Vi and Vj is less than or equal to Eij of r. That number, that smallest r, will give you beta ij. Okay? At least we're somewhere now. I'm going to give you a lemma without proof, because the proof is really just a matter of working out the details. It's really nothing too interesting. Here's the lemma. If Fi0 is less than or equal to Fj Uj, then my Eij of R, I'm just specifying how to compute Eij, is going to be the following. It's going to be Fi inverse of R plus Fj inverse of R. Whenever R is in the range from Aij to Fi of Ui, then it becomes Ui plus Fj inverse when R is between Fi Ui and Fj Uj. Finally, it will be Ui plus Uj when R is greater than Uj. Again, equalities can be included in all of them because they will output the same thing. All right, that's part A of the lemma. Part B. There's a mistake here. Let's change this because I think I made a printing mistake. This is supposed to be I here. That's supposed to be J. Okay. Please change that. And this is the reverse of that case. Yes.
We assume that Fi ui is less than or equal to Fj uj. All indices such that I is less than j. And also assume that maximum of Fi0 and Fj0 is always Fj0 for indices such that I is less than, strictly less than j. Isn't it too restrictive? Because we may not be meeting these two conditions. I mean the left part of the table.
This one?
No. The left side.
Which left side?
Yes. Aij. Aij is always Fj0 for indices.
If I is less than j, yes.
Yes, but we also assume that Fj uj is greater than or equal to Fi ui. I mean, these two conditions, I think, may not always be met at the same time for a specific problem. And do we really need Aij to be Fj0 for I less than j? I think we need the left part, but we don't.
Oh, you're right. Sorry, you have a point. For some reason, I was thinking of this. For that reason, I put it down. But no, you don't need this. Yeah, and that would be a mistake to put it down. There's no implication for that. You're right. Yeah, I don't know why my mind switched to that as I was writing, but there's no relationship. Yeah. This can be anything, either one. Okay? Good. Now that means you're following everything. Yes. Good. All right. So over here, let me just draw some pictures for you. Except that we're going to run out of time, so you can see the pictures in the book chapter that I referenced before. Okay, the 1990 book edited by Merchandani and Francis, and there was a chapter in it, and there are some good pictures illustrating what these functions look like. So it's good for you to take a look at those pictures. Okay. But let me just go on with the next lemma. From EIJR definition, well, not definition, but computation of EIJR, either using this expression or that expression, only one of them will apply, depending on if you have this inequality or the other inequality. These are mutually exclusive cases, exhaustive cases. Now, if you look at this particular expression, you can see that for R going from the lower value Aij to the value Fj actually there's a switch in the at the value Fiui, okay, from one expression to another one. You can see that both of these functions are monotone increasing because this is the sum of two monotone increasing functions, Fi inverse and Fj inverse. The other one is a constant plus a monotone increasing function, so it has to be monotone increasing. I'm not talking about this. This is a flat function. It's constant. Okay? So, for restriction of R between Aij and Fjuj, this function is invertible. That's the important idea here. Similarly here, when you restrict R to Aij to Fjuj, which is the same range as in here, again, this would be a monotone increasing function. So its inverse will exist at that at those values. So here's the result then. Again, referring to the case A or case B, Aij inverse, Eij inverse rather, of y is the inverse of that or that. So it will be Fi inverse plus Fj inverse evaluated at y. This is the inverse of this first expression. If yeah. This is supposed to be I here, so change that. My God, this looks extremely complicated from a distance. Nevertheless, we have to run through that. Okay. Part B. So either way, it tells you what the restriction of Eij are to the invertible portion of the intervals gives out as inverses. Okay? I made sure here that y is in the proper interval in order for the inverse to exist. Okay? Those will actually ensure that. Again, you have to do this when you're studying. You have to do this on the side, being very careful with all these domains and ranges and working out all the details, because this is all worked out, but then it may not be too easy to see it immediately. Let me give you the final lemma, which is the important one. the computation of beta ij. This will be either aij if the distance between I and j is less than or equal to eij of aij. Just a second. Yes.
Is it Tansel or is it?
Are you talking about this one?
Yes.
It's non-empty.
This one.
Ah. S1, yeah. S1. It's the third hour. That's why I start making mistakes. Too much work, yes. All right, yeah, assuming that the feasible set is non-empty, then beta ij is computable in this way. Well, this is really straightforward. It will be aij. First of all, you need to know how to compute eij, evaluated at aij, and that's straightforward from the definition. Once you check this condition, if this holds, then it will be the larger of fi0 or fj0. In the remaining case, it will be simply eij inverse evaluated at that. That's why we needed the inverse function over there. Okay. Okay, so I'm going to stop here, and the exam will be on Wednesday next week. So for the exam, you will surely master all details of how to compute these things. Huh? Yes. No.